Good morning. So first announcement, we have one more homework, the last one, due next week, Thursday. It's pretty short, so it won't take too much of the time. Just one question and 4 sub-questions. We are coming to the end of the material pretty soon, so we have one kind of cover topic to cover today. It's related to sensitivity analysis, and next week we'll cover game theory, so some basic material in game theory, and then I hope we'll have some time to make some review before the final exam. So that's the time for the rest of the term. The midterm will mostly did okay. The average was, I would say, a little bit lower than the first midterm. The marking was a little less harsh than the first midterm also. Somehow the first problem was, well, he did very, very well on average. Second problem, well, maybe it should review a little bit about the revised Stiglitz algorithm. I would say about half of it should review. Okay, so back to our material, we were talking the time before the midterm about sensitivity analysis. You start with the problem, you end up with some solution to this problem. Now you realize that the initial problem was actually not quite correct. You have to make some adjustments, and we discussed that different kinds of adjustments lead to different kinds of changes in the final tableau, and then you can readjust from there. If the adjustment is in the row coefficients in the objective function, well, you should perform several steps of the Stiglitz algorithm. If the change is in the right-hand side coefficients, well, you will get a solution which is sort of optimal but not feasible, and then you have to perform several steps of the dual Stiglitz algorithm. And today we'll cover a variation of this topic. So we'll talk about parametric linear programming. So let me start with the problem, the original problem, and then I'll tell what kind of changes we'll discuss. So the original problem is to maximize z, which is 10x1 plus 12x2 plus 7x3 subject to x1 plus 2x2 plus 2x3 is equal to 30. Sorry, plus 3x3 is equal to 30. And x1 plus x2 plus x3 is at most 20. And I also use the solution to this problem, final tableau. Is 0, 1, 2, 1, minus 1, 10, 1, 0, minus 1, minus 1, 2, 10. The optimum is 220. And is 0, 0, minus 7, minus 2, minus 8. These are the decision variables, these are the set variables. Alright, so this is a solved problem. Suppose you started with this problem, well, you were optimizing some, I don't know, some production facility. These were the constraints on the resources, that was your problem, and well, we decided that this is the answer. x2 is equal to 10, x1 is equal to 10. Now somehow, well, you are trying to optimize, let's say, not one production facility, but several of them. You own a whole lot of factories, and well, in each individual one you can make some decisions. The decisions is not only about the internal processes inside of the factory, how do you allocate your machinery to production of different kinds of products, X1 instead of X3, but you also can make decisions about, let's say, divert some resources from one factory to another one. So let's say that you have an option of taking some resources away from factory number 2, but somehow if you take away resource number 1, you'll have to give it resource number 2 in some amount. So this will affect the right-hand sides, but not in any way in some kind of predictable way. Or let's say another situation. You are trying to decide on your budget for advertising, and once you advertise, you know that the amount of profit will change. But because the products are, say, replacements of each other, if you advertise one of them, the profit for the other one will drop. But the profit for the one that you are advertising will increase. So also, you'll have some kind of situation where the coefficients, these 10, 12, and 7, are changing, but they are changing in interdependent way. And then the question is, well, you're trying to decide what is your advertising budget and trying to find the change which will lead to the largest objective function. Something of this kind. Well, let's discuss a problem of this kind. So, question. If z of t is 10 minus t x1 plus 12 plus t x2 plus 7 plus 2t x3, for t is positive, find z of t, the optimum solution. So here you decide to advertise this product kind of the most aggressively. So you get for every $1 of spending, you get 2t, well, for 1 million of spending of t, you get that much profit from sale of each one unit of X3. This one gets a little less publicity, and this one gets kind of negative publicity as a result of your own campaign. So the profit from the sale of X1 drops. And the question is, well, suppose you decided on some budget for advertising T. What is the new objective function? What is the new optimal solution? So that was kind of the story behind it. The mathematics is just, well, you used to have one objective function and now it's changing, and the dependence on the parameter is like here. It is some kind of linear dependence. And the question is, of course, find the new optimum. Find the new optimal solution. Well, in fact, we know how to deal with this. We do know how to deal with changing the coefficients of the objective function. We know that all we have to do is, well, update the final table. So let's do this. Update the final table. So first of all, our change is only in the coefficients of the last row. It's not inside of the matrix of coefficients. It doesn't concern the vector of right-hand sides. So the only change that will flow to the end will be in the last row. So let's recall how do we compute the coefficients in the last row. If you have some coefficient in the original table, to compute it, to compute the coefficient in the last table, we find such thing. CV, the inverse times ith column, and that's the coefficient in the last table. So now we are changing this part, we are changing the coefficients in the original table, so we'll change it to some updated ones. So let's see. Our coefficient, let's say first one, used to be 10. Now it got updated to 10 minus t. How will this change flow inside of this formula? Well, this number will stay unchanged. I'm not changing the inverse, I'm not changing n. So we are sort of changing CB, but we discussed this, this kind of strategy that we'll first update as if all the changes were for non-basic variables. We'll get a table where what used to be the basic variables are no longer basic variables, but then we'll do some kind of pivoting or some kind of row operations to reintroduce these basic variables. So we discussed that it's usually better to regard the change in two steps. First, regard it as if all the changes are only in the non-basic variables, and then do row operations to reintroduce the basic variables. So we will not change these things. So this will stay as it was. This coefficient, well, it used to be 10, now it will become 10 minus t. So the whole change will be from the old expression, subtract 10. Subtract t. So a new table will be as follows. The coefficients everywhere are exactly what they used to be. Minus 1, minus 1, 2, 10. But in the last row. In the last row, we used to have 0. Now it was updated, it should decrease by t. So this whole sum, non-updated, used to be 0. Let's say used to be 0. Now the updated one. So what is it? It is exactly what it used to be, plus this difference. So this difference is minus t, and the old coefficient is 0. So what I'm trying to say is that this change in the last row propagates linearly. If you decrease the first coefficient by t, in the final table it will still decrease by t. Similarly about all the other coefficients. So you see that this formula doesn't depend on the index that I get. So if the second coefficient increases by t, this one will increase by t. It used to be 0, now it's t. Third coefficient increased by 2t. It used to be minus 7, so now it's minus 7 plus 2t. Fourth and fifth coefficients didn't change in the adjective function, so we still copy them to the table. Well, this amount is going to change. So we are changing the objective function. So even though we still have x2 is equal to 10, x1 is equal to 10, x3 equal to 0, this amount will be readjusted. In fact, we can see how. So it will be minus, the new amount is 10 times, so x1 is 10, so 10 times 10 minus t, plus 10 times 12 plus t. So now in the brackets, 100, 220, minus 10t and plus 10t. Okay, so by some coincidence it does not represent t, but in general it should be 20t. Okay, So that's the update to the final table, which, as I said, we made this update, but we did not care about kind of the update in the basic columns. We did not care that the actual change in coefficients was among all others in the basic columns as well. And we are now going to pay some price for this. These coefficients in the actual table where these variables are basic should be 0. They are not 0. They are minus t and t. Well, we'll update this. So we'll make some row operation. We'll make it 0, and we'll make it 0. What kind of row operation? Well, of course, add t times the second row to the last one, and subtract t times the first row from the last one. So I want to kill these two coefficients. I want to make these columns actually basic columns. So that's the update that I have to make. Once again, before I erase this final table, I want to reiterate this idea that in this formula, the coefficients which are changing appear only in one place, right here. And they appear as just a copy of what they used to be. So the change in the objective function propagates in the following way. If you increase this coefficient by some amount, the coefficient of x1, it will lead to an increase of this number by the same amount. Of course, you can just apply this formula directly. You can actually compute this times this times this and subtract from the new coefficient, but it is kind of too much work. This thing is a kind of computational shortcut, and it's very useful. So it's an important idea that these formulas depend linearly on the actual terms that appear here, and hence the changes in the numbers also propagate linearly. In this case, it's just very simple. This coefficient appears just as it was, so every unit of increase here propagates the unit of increase right here. Alright, so we have this table. Let's make this coefficient 0. Once again, I'll copy all the other numbers. 1, 0, 10. Here I will get 0 and 0. Over here, used to be minus 7 plus 2t. I will add t times this row, so it will amount to subtracting t, and I will subtract t times this row, so subtract 2 times t, so it will be minus 7 minus t. Here it used to be minus 2. Now I'm adding t times this, so minus 2 minus t, and subtracting t times this. So minus 2 minus 2t. And here it used to be minus 8. Now I'm adding t times this, so minus 8 plus 2t, and subtracting t times this, so it will be minus 8 plus 3t. And the same happens here. I'm adding this times t, so minus 220 plus 10t, and subtracting this times t, so minus 10t. Okay, so here it doesn't change. Still z minus 220. Okay. So this is the updated final table where these variables are actually basic. x1, x2, and besides x2 and x1 are other basic variables. But now here there is some problem. Well, a small problem. These numbers are positive, so we know that the solution that we get is feasible. These numbers, are they positive, are they negative? Well, they look somewhat funny. Minus 7, minus t. Is it positive, is it negative?
It's negative because we assume t is positive.
Okay, right. So we made some assumption about t. It was t is positive. So let's say t was an advertising budget and we cannot spend negative amount. So that was our assumption. So minus 7 minus t is indeed negative. Similarly, minus 2 minus 2t is also negative. Well, minus 8 plus 3t, well, not necessarily negative. If t is small, let's say 0, this number is minus 8. So it is negative, and we have the actual solution written right here. If it is large enough, let's say 5, then you'll get minus 8 plus 15, so 5, 7, and here you'll get a positive coefficient. And then you'll have to make, well, another step in the simplex algorithm. This solution will not be optimal. Well, if this is the case, that's what they're going to do. So what we'll do is, if this number is negative, the solution is this one. x1 is equal to 10, x2 equal to 10, x3 equal to 0, then star of t, the optimum is 220. But only under this assumption. So for t, which is between 0 and here we get t smaller or equal than 8/3. Our objective function is still 220. So we cannot increase the objective function if our advertising budget is from 0 to 8/3. Once it gets larger than 8/3, this number then turns positive. And then we can increase the objective function. So if t is greater than 8/3, well, make minus 8 plus 3t will become positive. So we have to re-optimize. So under these conditions, once you get to this, well, what used to be the final table, it's no longer final. This number is positive. So we'll do the update of this. This will be our pivot column, because this number is positive. Which row will be the pivot row? Well, this was positive portion here, 10/2. And then we'll make the actual pivot. So let's try not to do too many computations if they are not strictly necessary. So I know that I should get a feasible solution. Simplex algorithm always goes from a feasible solution to another feasible solution. It might or might not be optimal, so we'll have to compute these numbers in the updated table to find out whether it is optimal. So what happens here, I'll have to take this row and add to this a multiple of that one, each multiple. I'll have to multiply this by 4 minus 3 halves of t. So this will be the third row plus the second row times 4 minus 3 halves of t. Okay, so it will be 4 minus 3 halves of t. First entry, second entry is 0, third entry is minus 7 minus t, minus 4, so minus 11, and plus 3 halves of t, plus t over 2. Next one, minus 2, minus 4, so minus 6, minus 2t, and plus 3 halves of t, so minus t over 2. This one should be 0, and this will be z minus 220 plus 4 times 10, so minus 180, and minus 3 halves of t times 10, so it's minus 15t. The right hand sides are, I should divide this by 2. This one, I should add 1 half of the second row to the first one, so it will be 15. 0, 1. Sorry, 1, 0. Okay, so that's the updated table after I made the pivot. Okay, so what do we see? We see that oh no, it's alright. This number, what about it? Is it positive or is it negative?
We made an assumption that t is greater than 8 over 3, so it's still negative.
It is still negative, right? So this number is negative. 4 minus 3 halves of t is in fact negative for t which is greater than 8 over 3. That's exactly how the simplex algorithm should work. If this coefficient turned out to be positive even when t is equal to exactly 8 over 3, well, then we made some mistake. It should have become negative, at least when t is just a little bit larger than 8 thirds. Might not be always negative, but it should be at least negative in some range. This number is 0. This number, so for some reason it is not always negative, which is kind of strange because before I thought it was always negative. But anyway, so if we did not make a mistake, an arithmetical mistake, which I don't know how likely it is, but anyway, so if minus 11 plus t over 2 is negative, so this number is also negative. Minus 6 minus t over 2 is negative, no, for very simple reason, t is just negative. So if this number is negative as well, i.e. t is at most 22, then the optimal solution x5 equal to 5, and this was x2. x2 is equal to 15, x5 equal to 5, and our objective function is 180 plus 15. Well, then we still face the option that this assumption is not correct, that t isn't greater than 22. No. If t is greater than 22, do one more thing. So we'll have to go back to this table. We'll have to make a pivot with this column as a pivot column. Which row? Well, we'll have to actually compute these two numbers to find out. So this was minus 1/2, and this was here I should add 1/2 to the second one. So do the 3/2. So I see that the smallest positive quotient is this one. In fact, it's the only positive quotient. And then I'll make another pivot. So I'll get I hope it will be the last one. Also, we have to compute the whole first row to make the actual pivot. So let's go back to here and compute the first row. So it's this plus 1/2 of the second row, 1/2. This one will be 1 minus 1/2, so 1/2, 0. So we'll have to take the first row, take the third row, and we would multiply the first row. 2/3 times 11, so it will be 22/3. That will kill the minus 11, and to kill the t over 2, we have to multiply by t over 3. So minus t over 3. We'll get some answers here. So t plus 3, so plus 11 minus 3. So let me just write it like this. 4 minus 3/2 of t plus 1/2 times 22 over 3 minus t over 3. Let me try to do as few computations in my head as possible to avoid as many errors as possible. So the second one will be 22 over 3 minus t over 3. Next one will be 0. Next one will be minus 6 minus t by 3 minus 1/2 times this. It's a plus 1/2 times 22 over 3 minus t over 3. And last one will be 0. So even here, I do see that these numbers are all negative. So this one is the last pivot. How do I see? This number is negative because we know that t is greater than 8/3, so this part is negative. This part is negative because I assume that t is at least 22. So both these numbers are negative, their sum is negative. This one is negative because t is greater than 22. This number is negative because t is positive. This number is negative because t is at least 22. So the sum is negative. And finally here we'll get something. So minus 180 minus 15t and plus 23/3 minus t over 3 times 15. And we'll get our new basis will be 1, 0 here. Sorry. 1, 0 here. And 0, 1. So finally we get the complete answer. We now covered the whole range of possibilities for t. When t is from 0 to 8/3, we didn't have to make any pivot, and our solution was 220 as it used to be. So let's summarize it somewhere. So answer, if t is from 0 to 8/3, well, our solution is x1 is 10, x2 is 10, x3 is equal to 0, and the objective function is 220. If t is from 8/3 to 22, our solution was x1 is 0, x2 is 15, x3 is 0. The objective function was 180 plus 15t. And finally, if t is greater than 22, our solution is x1 is 0, x2 is 0, x3 is, okay, we have to find out what this number is. So we take the first row and add 3 times the second one. Oh no, that was the pivot row, so I should just multiply it by 2/3. So our solution is x1 is 0, x2 is 0, x3 is 10, and our objective function is what we get is then this, so minus 180, 15, 5 times 10 to 110, 70, minus 15t, and minus another 5t plus 20t. And now we'll have a chance to see, well, whether we made some mistakes in the computation, and I'm afraid we did. We'll see it right now. There is a way to check that the answer makes some sense. You know, our problem is a linear programming problem. The dependence on more or less everything is linear. On every kind of coefficient, it's linear. So what happens is, if you change the coefficient slightly, it will propagate the final tableau, well, as a small change. So the answer should change slightly. You should not expect any discontinuous jumps. So this solution, even though it looks like 3 different expressions, they should somehow glue in together to form some kind of smooth dependence on t. So let's see what we get. Let's plot the function z star of t. as a function of t. Well, we know that for t from 0 to 8/3, 8/3 is not very large, about 3. So 8/3. We get that the optimum is 220. So we get just a straight line like this. Next, we get a line with much larger slope, 15. Let's see what happens when t is exactly 8/3. We should expect that they will somehow match. Let's see. When t is 8/3, 8/3 times 15, so it's 5 times 8, 40. 40 plus 180. Okay, miraculously it is 220. So we get a line that starts from here and goes up with a slope of 15. So make it visually a little smaller. And this goes on all the way until we hit 22. Just because I don't have enough space, I make 22 look much closer than it should be. Okay. As we reach 22, this function, well, it used to be, it is 180 plus 22 times 15. So it is 330 plus 180, 510. Well, from here we should plot this function, 70 plus 20t. Well, it will have even larger slope than 15. This has slope 15. Next one should have slope 22, and if we did not make a mistake, it should pass through this point. Let's see. So 22 times 20, 440, plus 70, 510. Okay, it does. So here we have such a function. Slope 20. And this goes on all the way to infinity.
Yeah, what's that? The second line you drew? Like,
This one?
the one with, to the left. You have 3 lines.
This one.
Yeah, no, the one. Sorry.
Okay, this one, and that one.
But there's another one. What's that?
It's a wrist.
What's that?
It's a wrist.
Oh, okay.
Oh, this one, yes. I realized that if I make the slope too high, I won't fit everything. So then I erased it. Okay, so here we have the dependence of the optimal solution on the parameter t. So we see that for t, which is small, we have this segment, which is 220. For t from here to here, we have this thing, 180 plus 15t. And for t, which is very large, we have this 70 plus 20t. And, well, as a way to check that your calculations are at least reasonable, you should check that indeed you do have discontinuity. Another thing, well, one observation is whenever you make a change to the coefficients in the objective function, well, a continuous change, you will expect that the optimal solution will be still a continuous function. Another thing, if the dependence on the change is linear, so like we had our dependence on the parameter was 10 minus t, some 12 plus t, and 7 plus 2t. So we had a dependence on t which was linear, a number times t. So it will propagate, well, as a linear change in the objective function, but not quite. Because we have to make some pivots in some cases, it will be linear, but only in some particular ranges. So we'll get a piecewise linear function. So let me make general observations. If dependence on the parameter t is continuous, you should expect the optimal function to be continuous. To be continuous. If it is linear, you should expect the optimal function to be piecewise linear. So we have the graph will consist of lines, but not just one line, maybe several lines stitched together. And finally, it will always be what's called a function which is concave up. Let me explain this way. So, what is this graph about? We have a function, the objective function, if you recall, is, well, 10 minus t times x1 plus 12 plus t times x2 plus, well, similar thing times x3. When we do the pivoting, we'll get some solutions which actually do not depend on the parameter t. So the actual variables x1, x2, x3 will be some numbers. Let's say here x2 is equal to 15, x3 is equal to, sorry, x3 is equal to 15, x1, x2 are equal to 0. They do not depend on t. So if the change was only in the last row, the actual solutions do not depend on t. They depend on t only in the fact that, well, as t changes, as it passes this point, well, the optimal solution suddenly jumps. It used to be 10, 10, here it is 15, 5. And here actually they somehow give the same objective function. So what happens is, suppose that you explore whether the solution where x1, x2 are basic, rather x2 and x1 are basic, is the optimal solution. Well, if it is, then you'll get that the objective function is 220. You'll just plug in 10, 10, 0 into x1, x2, x3, you'll get some expression for the objective function. Well, it is this line. Then you explore whether the solution where x2 and x5 are basic, so like over there, and you'll find out that the objective function is this one. So if you plug in x1 equal to 0, x2 equal to 15, x3 equal to 0, you'll get the objective function, which is 15 times 12 plus t. So just take these numbers, plug them into the original objective function. You'll get a line. Well, in what range will this line be better than this line? Well, of course, when it's higher up than this line. So, I can draw another graph. And write down all the ideas that they said in words. So, our objective function as a function of t is, I think it was something like this, 10 minus t x1 plus t x2 plus 7 plus 2t x3. So if x1 is equal to 10, x2 equal to 10, our function is 220. So if we explore the solution corresponding to this basis, our objective function is like this. If x1 is equal to 0, x2 equal to 15, x3 equal to 0, you'll get a function, the objective function will be 12 plus t times 15. And finally, if we explore this solution, x1 x1 equal to 0, x2 equal to 0, x3 equal to 10, our objective function will be 10 times 2t. So we have, if our basis is like this, the objective function is like this. If the basis is like this, the objective function is like this. And so on. So we get, for each basis, we get some line for the graph of the objective function. Which of these bases is the optimal and in what kind of range? Well, that's easy to answer if you can just imagine yourself drawing these functions. So here's the graph of 220. Here's the graph of 12 plus t times 15. Here's the graph of 10 times 7 plus 2t. Maybe there are some other lines. Maybe in some other basis, you'll get some other value for the objective function, maybe something like this. Let's say x1 is basic and x2, x3 equal to 0, maybe you'll get some kind of subset. What will be the actual optimal function? Well, of course, for each value of t, it will be the function which is the largest one. So all you have to do is just take the largest linear function which appears here. So that will be the optimal graph. And of course, if you take a bunch of lines and you take this operation of, well, at each point find the highest one, you will get something which is convex out, something which looks like this.
This is a technical question. We assume t is negative, so can you extend your graph like that, even for negative t?
So as I said, we might get some extra kind of line like this.
Oh.
So I don't know whether we will get something like this. It still must be concave up, yes. Maybe actually we'll get something like this, maybe maybe 2 breaks or 5 breaks, so I'm not quite sure about the quantitative version of this graph, but qualitatively it must consist of lines, they must match together, and the whole thing should be concave up, just because I'm taking the highest line of all the lines which appear on the picture. So the last point is so change is linear and is in coefficients of z, then the dependence on of the objective function on t, this function is concave up. Like this. So we have a function which is concave up, concave down will be the opposite of it. Alright, so this covers the dependence, the changes in the coefficients of the objective functions. Maybe any questions about this kind of change? So it doesn't matter because you see when t is equal to 22, we should get two expressions which give the same answer. And when t is equal to 22, yes, it is true that we get two different solutions. So in fact, when t is exactly equal to 22, we have not just two solutions, we have infinitely many. We have a way to join this solution with this solution continuously, but still get the same value of the objective function. Because you see, these two lines match exactly here. So if t is equal exactly to 22, well, in this pivot, which we made from here to here. This pivot will actually be a degenerate pivot. It will not change the value of the objective function. It will change the solution, but not the objective function. But when this t is strictly larger than 22, we get only one solution, this one. Okay, so let me discuss another kind of change, which is maybe even more common. So we'll have 8 traces of the original problem. So let me recall the original problem. The original problem was 1, 2, 3, 0, 0, 30. 1, 1, 0, 1, 10. Z was 10, 12, 7. And the final table was 0, 1, 2, 1, minus 1, 10. 1, 0, minus 1, minus 1. To 10 and Z 120 minus 7 minus 2 minus 8. So that was the original formulation of the problem. The original problem was like this, the final table was like this. And now I want to discuss a change in the right hand side. So if the right hand side change to 30 plus 2t and 20 minus t. So the so we used to be 30, 20, and now we are doing the following. So let's say the first constraint was about some resource, metal, second one was about another resource, plastic, and now you are re-optimizing your whole business, and you say, well, I can use a little bit less of metal in one factory and reallocate it to this factory. But also, if I use a little bit less metal there, I'll have to use a little more plastic as a substitute. And then I'll have to take a little bit of plastic from this production. And the question is, well, once we update to these new values of the amount of available resources, what will be the new objective function? What will be the new optimal production policy? And once again, let's say that we're only discussing changes when t is greater than 0. What is the new optimum? Okay, let's see what happens to the right hand side. What happens is my right hand side gets changed from 30, 20 to 30, 20 plus 2t minus 10. That's my change in the right hand side. What happens to the updated right hand side? The right hand side in the final table. Well, I know what they are. They are the inverse times the original right hand side, and the inverse, I should be able to find it in the last table, in the last 2 rows in fact of the 2 columns of the final table. So new right hand side should get updated from this -1 minus 2. This is the inverse times 30, 20. This should get updated to this plus 3t minus t. So that was my right hand side in the original table. To get to the final table, I have to multiply by the inverse. Well, if this got updated to this, well, this will get updated to this. I'll still multiply both this thing by the inverse. The good news is I don't have to perform this computation. It is already performed for me. Because this is exactly the original right hand side. So this is 10, 10. I copy it from the last column over there. Plus, well, here I will have to make some adjustment. So 2t minus t is 3t, minus 2t and plus 2t, 0. Oh. Okay, thanks. So, yes, it is 2. Thanks a lot. So this will be 2t plus t 3t, and this will be minus 2t minus 4t. Thanks a lot. Okay, so my new right hand sides are 10 plus 3t and 10 minus 4t. So my new final table is what it used to be 0, 1, 2, 1, minus 1. But now it will be 10 plus 3t, 1, 0, minus 1, minus 1, 2, 10 minus 4t. The coefficients don't change, minus 7, minus 2, minus 8. The objective function shouldn't change. Well, yes, it should. So our new solution is 10 minus 14 and 10 plus 14, 0. So if we plug it into the original objective function, which was 10 times x1, 12 x2, and 7 x3, we'll get 220, 10 times x1, so minus 40t, and 12 times x2, so minus 40, and plus 36, minus 40. So this is my new final table. After I made the change, this is my new final table. Well, it is the final table if my new solution is actually feasible and optimal. It is optimal. These numbers are negative. Is it feasible? Well, not always. You see, this number is positive. 10 plus 3t is positive. So for t which is positive, 10 plus 3t is definitely positive. So if the second thing is positive, 10 minus 4t is positive, we get the solution. And the solution is x1 is 10 minus 4t, x2 is 10 plus 3t, and my function is 220 minus 40, a plus 40. So if t is at most 5 halves, we do get the solution. But if t is greater than 5 halves, well, this number will be negative. N minus 4t will be negative. Our solution will not be feasible. So what should we do?
Can we treat basic variables as non-basic?
Basic variables is non-basic.
Then you get your test one.
But we do have basic variables.
Then it's the wrong basis.
Yes, it is the wrong
Oh, dual
basis.
simplex.
Yes, we'll do the dual simplex method. So we do have a way to go from a solution which is kind of optimal, but it's not even a solution, not feasible, to a solution which is feasible and optimal. And that's the dual simplex method. So let's perform this. So we'll perform dual simplex iteration. So let's recall how the dual simplex algorithm works. You first decide on the entering row, the pivot row. It corresponds to the most negative number on the right hand side. Here we have just 1, then minus 4t. This will be the pivot row. The pivot column corresponds to the smallest positive quotient here. Let's see what is the smallest positive one. 0, 0, 7, 2, and negative number. So 2 is the smallest positive quotient. So we get this column as the pivot column. And then we perform natural iteration. Natural pivot. So once again, let me try to make these two computations as possible, and then, well, if they are not enough, I'll compute even more. So here it will get updated to 4t minus 10. I multiply the second row by minus 1. I add the second row to the first one, and get 20 minus t. I'll get here z, so I'll take the second row and subtract 2 times the second row from the third one. So z minus 240 minus 4t and plus 4t. 1, 0, 0. 1, 0. Alright. So I see that this number is now positive. 4t minus 10, when t is larger than 5 halves, this number is positive. This number, well, not quite. It could be positive, could be negative. So if t is just a little bit larger than 5 halves, this number will be positive. If t is really large, if it is larger than 20, it will be negative. So for t between 5 halves and 20, the solution is this one. So this was x2, this 20 minus 2, x4 is 4t minus 10. And my optimal function, optimum objective function is 240 minus 40. Well, unfortunately, I still have to consider one more case, when t is larger than 20. So let's consider this case as well. If t is larger than 20, we'll have to make one more step of the dual simplex algorithm. This time This row will be the pivot row. So I have to compute these coefficients. And for the pivot column, I'll have to decide on the smallest positive quotient, so I'll have to compute these coefficients as well. So let's do this. For this one, I'll have to add to the first row the second one. So that will be 1, 1, 1, 0, 1. Okay, very convenient coefficients. This one, I should subtract 2 times the second row. So it will be minus 2, 0, minus 5, minus 8, minus 2 times 2, minus 2. So these coefficients are still negative. Of course they are negative. That's how the dual simple algorithm works. It always keeps my solution optimal and it makes it more and more feasible. So the smallest positive quotient is, let's see, minus 2 over 1, minus 5 over 1, minus 12 over 1. So which is the smallest positive quotient? They're all negative. So we can't make no living variable in the dual simple algorithm. Sorry, there is a living variable, no n-living variable. So what does it mean? So we are trying to decide how much will increase some variable, and we see that, well, you can increase it as much as you can, as you want, as much as you want, as much as you want. But remember that this is about the dual problem. So the dual problem is unbounded. What does it tell you about the primal problem? It's infeasible. So we see that the dual is unbounded, hence the primal is infeasible. So let's draw the function z star of t as a function of t. So now we know what happens to any kind of parameter. If t is from 0 to 5/2, the objective function is 220 minus 4 plus 14. 120. Here the slope is 14. And the derivative is plus 14. That's the first solution.
Oh, that's the second one.
The second one is 240 minus 14. And this goes all the way until we hit 20. When t is equal to 20, we get 240 minus 20 times 240 minus 4 times 20. 160. 160. It's not what I expect. So probably made some mistake. Okay, and from here, from 20, we should not draw anything. So here we don't have a solution. No solution. The reason I'm saying that we made a mistake, and I'm quite sure that we actually made a mistake, this number should have been 0. Why? So think about how we got to this non-feasibility part. We updated the right-hand side to, if you recall, 30 plus, let's update 30 plus 50 and 20 minus t. And the second constraint was about x1 plus x2 plus x3 being at most 20 minus t. So of course when t is greater than 20 you don't get any feasible solution. Because the second constraint got updated to sum of positive numbers is smaller than a negative number. So that's the reason why this solution is not feasible.
So you have 220 plus 40 there, but when you t is 5 over 2, you have 230.
5 halves times, yes.
That's not.
But then 240 minus 40 is, oh yes, this is 30, yes. But this does match, because 240 minus 4 times 5 halves is still this. Somehow this doesn't work. So we probably made a mistake. So once again, the reason I'm saying that we made a mistake is when t is really large, this number in the second constraint is negative. And we have sum of positive numbers is negative, of course it is not feasible. We will not get a feasible solution. When t is exactly 20, so right here, we should get x1 plus x2 plus x3 is more or equal than 0, hence all of them must be 0, hence the objective function is 0. Well, unfortunately, we did make some mistakes, so I would think that it would actually look like this, and this slope will be different one. Here, integrating minus 40. I have no idea how to go here. So probably, yes, probably you're right. Probably there was some mistake. Quite likely it was some sign. But I erased enough of it so that we won't be able to trace a mistake.
So there's no such thing as concavity here or something?
There is concavity. So here what happens is every time we do some pivot, we are making our function, objective function smaller because it's a pivot of the dual simplex algorithm. So we switch from a line to a line which is even smaller than the previous one. So as we go from left to right, the slope of the line becomes smaller and smaller. So here the solution is always concave down. So this thing is linear and concave down. And that's once again something quite general. Once you perform the dual simplex algorithm, you get concavity down. So once the changes in the resources in the right hand side, you get this linear solution which is concave down. So typically there will be some particular way to allocate resources which will give you the maximum. You would expect a function which is concave down to have either to have a maximum or to be unbounded. Alright, so see you next time, and next time we'll discuss quite different topic. It will be a game.